Okay, I think we can get started. Today we will introduce a new paper. It talks about the generative Bayesian deep learning for semi-supervised image segmentation. Here is a brief overview of this paper. It introduces a two-stage training approach, and it also uses a generative Bayesian model to learn the general distribution of input image and also the mask label instead of just learning the distribution of input image as in regular autoencoder. The third point is this paper uses the generative input and also the mask label to train a segmentation model for downstream tasks. And the performance achieved by this approach is pretty good. It achieved a dice score of 0.91. And the limitations include firstly, it only achieves a marginal improvement over existing state-of-the-art performance, and it does not show any visualization of the segmentation result. The intuition behind the approach is that based on the existing variation autoencode architecture, a new branch is added for learning labels during the training process. Just as this name indicates, it has some labeled data, and this new branch can help learn from this labeled data here. And this paper is published in 2022 at the computer vision and the pattern recognition. So the starting point of this paper is like this. First, it considers the general distribution of input image and the mask label and derive an evidence lower bound. And in practice, this evidence lower bound is calculated via this new formulation in equation 7. So it contains totally three components. The first one corresponds to the conditional distribution of the mask label. This it's the combination of cross entropy loss and also dash loss. And the second term is the mean square error loss. It corresponds to the conditional distribution of conditional probability of image given the latent variable z. And the third one is the KL divergence between a posterior distribution of latent variable and its prior distribution. So if you look at the original formulation, the three terms have pretty good interpretation. The first one is the expectation of the conditional distribution of y given the input image and also the latent variable. And second term is the conditional distribution of input image given the latent variable z. Third one is the ratio between the probability, the posterior probability of z to the prior distribution of z. And in regular autoencoder models, the joint distribution of x and y is replaced by just the px, since we only have the input image, we don't have the label. Here the expectation is over this posterior distribution q z given x. So next we will introduce how these four terms are calculated in practice. First, here is the system architecture of this approach. So given input volume, you can think of it as a sequence of images. And this sequence of images will go through a 3D unit encoder, and we get a sequence of mean vectors, and each vector corresponds to one image slice. And we also have a sequence of covariance metrics, and each covariance metrics correspond to one particular slice. Then, as we usually do in variation autoencoder, we do this reparameterization. Use this to approximate the posterior distribution of this latent variable. Then from this latent variable distribution, posterior distribution, we sample a sequence of latent representations. We treat them as the representations of the input image slices. And this input, basically this latent representations will then go through the 3D unit decoder, and we get reconstructed images. And this reconstructed images will be combined with the original input images to calculate the mean square error loss. So this part is exactly the same as the variation autoencoder. The new thing here is this extra part. For example, when this sequence of images goes through another 3D unit encoder, we will get a sequence of feature maps, and we will combine this sequence of feature maps with the sequence of latent representations for all these images. We combine them together. We then throw them to a new 3D unit decoder, and we treat this as the condition. We treat the output as the basically we treat this model we use this model to learn the conditional distribution of the label conditioning on the input image and this latent variable. So for this mask, basically the label segmentation mask we get, we will combine it with the ground truth mask to calculate cross entropy loss and also this death loss. So here the covariance matrix in this paper, it's assumed to be a diagonal matrix, basically no correlation between these different latent variables. Yeah, as we just mentioned, the first branch of this system is exactly the same as risk-rational variation autoencoder training, and all the labeled input and the unlabeled input will be processed by this branch. But for the second branch, only the labeled data will be processed. Yeah, as is shown here. So far we have these three losses: the reconstruction loss and this segmentation loss. There's another loss here we need to consider. Basically, the KL divergence between the learned posterior distribution and the prior distribution. So the final loss is the weighted sum of these four losses. For this whole system, actually, this component it help us learn the posterior distribution of this Z, use the reparameterization technique, and for this part, it help us learn the joint distribution of Px and Y. So once this generating model is trained, we can use this model to generate the input volumes and also labels. And this generate the input volumes and labels will be used to train another 3D unit to get a segmentation model. And this segmentation model will be applied on other tasks to get the evaluation metrics. So as is shown in these tables, it achieves pretty good dice performance. For example, here it achieves a 0.911 dice score. So it's only marginal improvement over the existing style of data performance, but this number is pretty good already. Okay, that's all. Thank you.